Hello, hello. Is Harry there? Yeah, I can bring it up. No, he's not having technical problems. Yeah.
Yeah, hi, Nick.
Hi, James.
Oh, great. We've got Harry.
Oh, good.
So
Hi,
working
Harry.
now.
It's alive.
I hate this
That's
StreamYard. I'm sorry.
credit to Gene Wilder in Young Frankenstein. Harry seems to have no.
The
There he's moving.
StreamYard wouldn't let me start the stream. It had it defaulted to the last.
Oh.
Well, Harry, you can take the stage and start your presentation.
All right, you hear me now?
Yes.
Yes.
Can you hear me?
Yes.
Can you hear us, Harry?
The stream is. Yes, barely. There's something really badly messed up with StreamYard. I guess we can get going here if I can figure out how to do it.
I guess you have to share screen, Harry.
Oh, all right. Well, I had to restart my computer because I couldn't get into the green room.
Oh.
And now my presentation is all messed up because of I had to restart the computer. All right. Well, this is a good reason not to use StreamYard as far as I'm concerned.
Agreed.
It's gonna interrupt in a few minutes here.
Harry, do you have a fast internet connection? Like fiber optic?
You know, I do. So please stop bringing that up.
Yeah, but you were breaking up there for a while.
Yes, I know. It's StreamYard. That's the wrong one. All right. Can people see the screen? Can you see the screen? Can you hear me?
Yep. Yes.
Okay. Can you enlarge it?
So I'm on. Shall I get, huh?
If you can make it bigger, it'd be better. But
We can't hear you, Harry.
well, 44. Mhm.
Can you hear us, Harry?
Maybe the- that's,
Can you hear me now?
Yes,
Yes.
I can hear you now. I think you have to be up on the screen in order to be heard.
Can you hear me?
Yes.
Yeah. If you could make your
Well,
slide full
So
screen.
now the
in itself.
presentation done that. You know, if I would, if I could. All right. Okay. Do you hear me now? Can you hear me?
Yes,
Yes.
yes,
Hello.
Yeah,
yes.
we can hear you.
All right. I don't know how to make this screen bigger.
Well, it's okay as long as you don't go too far down on the page.
Oh, here we go. Oh, there we go. Can you hear me?
Yes.
Yeah, I can
That
hear
good?
you. And if you could get rid of the left panel
Well,
showing the
it's okay.
All
It's
right.
okay. It's depth, not width. That's maybe a problem.
well, that's good.
That's good.
Oh, that's even
All
better.
right. Well, I need that to change. All right. All right. So I appreciate you coming. Sorry, we're a half hour late.
You can
Something
use
went
the
wrong with
arrow key.
StreamYard. I don't know.
Use the arrow keys to move from slide to slide.
Well, all right. So I'm going to talk about the cosmic microwave background. And the reason I'm doing this is because the presentation I gave about the Lambda CDM cosmology, that raised a lot of issues in my mind about what the Lambda CDM was and how they were getting these results that they were claiming for dark matter, dark energy, and that sort of thing. And
Harry,
talk about, yes,
by the
what?
way, have you started recording?
Do I have to start recording?
I think so.
I don't see a button here that says start recording.
Okay.
I see
Okay.
no such button.
All right. I thought they were always saying
Where would the button be?
I have no idea. I just remember
I thought
people saying maybe it's automatic. Okay. Maybe it's automatic.
I don't know. I have, this is only the second time I've done that without any, and apparently there's no assistance being provided. So,
Yeah.
okay, so I'm going to talk about the so-called discovery of the microwave background. It's from the theoretical origin to the latest satellite results. Okay, so here, and if you go into the literature, you see some statements about the discovery of the microwave background. And I think this confused me. I thought I understood the cosmic microwave background and what it was about until I started reading. And the more I read, the more I got confused. So we have here that one statement I found, the hot model of the universe proposed by Gamow in 1946 was confirmed in the measurements of Penzias and Wilson, the significance of which was understood by Dickey. It's not real clear what they're trying to say there, but the implication is that Gamow proposed a theory of the microwave background. Well, it turns out he didn't. Then we have another statement, comes from another source. In 1965, Penzias and Wilson discovered an anomalous excess instrumental noise amounting to about 3K in a radio telescope. No local source for the radiation was found, and it was soon realized that this universal microwave background radiation was probably the remnant of the primeval fireball. That's sort of close to being correct, but it's still kind of vague in my view. So what is really going on here? And that's the question I was asking myself as I was looking at this. Here's another, this is from a history, and it says the existence of a cosmic microwave background was theoretically predicted by George Gamow and his associates. Okay, but played no role in the accidental discovery of the 2.7 degree cosmic microwave background radiation by Penzias and Wilson while they were testing a new type of satellite communications antenna. And then he talks about an earlier measurement of the cosmic microwave background went unnoticed by Russian scientists. And then, meanwhile, not far away, Robert Dickey and his colleagues at Princeton University were building a radiometer to verify Dickey's prediction that it might be possible to detect the microwave remnants of the Big Bang. But they were beaten by Penzias and Wilson's serendipitous Nobel Prize winning discovery that led to the final demise of the steady state theory. Now, this is kind of reasonably accurate, but it leads to some questions, like, for instance, at the top it says the existence of a cosmic microwave background was theoretically predicted by George Gamow. And I always thought that was true, and most people think that's true, but we'll find out that that's not really exactly correct. Okay. So I titled this, I was really originally going to talk about, as my title for this would be Cosmic Microwave Background Prediction, Discovery, or Mistake. And the reason I'm saying this is because it's kind of unclear exactly what happened historically. And the way it's presented in different sources of information, like, say, for Wikipedia and textbooks and different books, it's kind of confusing and kind of could be misleading to people who don't really understand what's going on. And so the first thing that happened was I went to look at the original papers that Gamow wrote. There was one of them was in 1946. I couldn't find where he said anything about microwave background or predicting anything about microwave background. Couldn't find that. And then it turns out that some other people point to a different paper as the primary paper, which was written by Alper and Herman in 1948. And in that paper of 1948, they correct Gamow's paper of 1946. So looks like Gamow was wrong what he said in 1946, and what they're saying in 1948 is correct. And I thought this was kind of interesting. Alper worked at Johns Hopkins Applied Physics Laboratory at this time. He had been apparently a student of Alper, and he was working at Johns Hopkins Applied Physics Laboratory, student of Gamow, sorry. And Alper was working at Johns Hopkins, and that was in Baltimore. I used to work at Johns Hopkins Applied Physics Laboratory, and while I was there, I never really heard much about this. You would have thought this would have been a big deal for them. So that kind of puzzled me when I heard about this. And anyway, so they're correcting the original Gamow article. And what they're saying is that there's this Big Bang origin creates this high temperature gas, and they come up with and this is the Alper paper, comes up with about 5K. That's their prediction, 5K. But they're referring to the remnant gas of the Big Bang. See, I emphasize in bold gas. Okay. And I couldn't see where they said anything about there being microwave background radiation produced by this Big Bang thing. So I found that to be somewhat curious. Here's a copy of, I quoted here, this is from the original Gamow paper, and I couldn't really find anything where they said anything about microwave background radiation in that paper. But really what he's saying is he's assuming that there's a bunch of neutrons created at the beginning, and they decay into electrons and protons. And so you get this hot fireball, which Hoyle later dubbed the Big Bang. Oops, and I'm moving too fast. Okay, I went way too far ahead. Okay, now I have a copy of a book by Dickey, and he gives a pretty good account, and it's kind of interesting why they sort of in the textbooks, in the orthodox interpretation, they downplay what the Princeton group did. And it's my opinion that the Princeton group should have been credited with the prediction of the cosmic microwave background radiation and its discovery. And so Dickey gives, in his account, he says that the hot cosmology, which we were talking about earlier, the Gamow and the Alper work that was done, had sort of fallen into disfavor. I'm not really sure that's really correct, or maybe people just weren't that interested in it, or they didn't get that much attention. He says that it was revitalized by a paper by Hoyle and Taylor. And that came out, I believe, about 1962. And they were trying to theorize what was the creation of helium in the universe. Now, Gamow and his group, they thought they could create all of the elements. And it turned out that they really weren't very successful in that the Big Bang would create all of the elements. And I think that may be one of the reasons why Dickey says the hot cosmology fell into disfavor, because they could only create the lighter elements, hydrogen and helium, but not of the real heavier elements. So it was later discovered that this really didn't explain the creation of all the elements. And so Hoyle and Taylor were reinvestigating the issue. And apparently this was the motivation for the Princeton team led by Dickey to look into the hot Big Bang idea. And so they came up with a different theory, and Jim Peebles, we'll hear a little bit more about Jim Peebles, and I believe he was probably a young student at the time. And I think he was asked to do some of the theoretical work by Dickey, and but they were mainly interested in what I think this is really important, is a cyclical oscillating universe. So the Princeton team independently suggested a hot origin of the universe in support of an oscillating universe. Such a universe seemed to require a hot bounce. So the innovation of the Princeton group was that they didn't have the problem of where did the material to form the universe that became manifest in the Big Bang come from. They had no problem with creating the universe and all the material and energy in the universe at t=0 at the moment of the Big Bang, because there was a cyclic universe, which was that the universe contracted down into a small volume and then became very hot, and it recreated itself at the moment of the Big Bang. So they thought this was an improvement on the original hot Big Bang idea. And Dickey calls this hot fireball. They refer to the Big Bang as the hot fireball. And they actually put forth the idea that there be this residual thermal black body radiation as a result of this. So as far as I could see, this is really where the idea of black body radiation created by this hot Big Bang comes from. And I think it was, from what I could see, it was the Princeton team that came up with this idea. And I think people believe that Jim Peebles, was the one who was doing a lot of the theoretical work behind this. Okay. And according to Dickey, continuing with Dickey's discussion in his book, he says, well, that once they had convinced themselves that this idea of a hot Big Bang made sense, or hot fireball made sense. This Wilkinson, who we're going to run into again, and Roll began looking for a signal. So they were basically putting together equipment, and figuring out what equipment they needed, and on the basis of the prediction that there would be a microwave background radiation that would be detectable, and they were doing this at microwave frequencies. Want to point out here that the WMAP satellite is, the W stands for Wilkinson. He died in 2002 and was chairman of the Princeton Physics Department, I believe. And he had continued working on the cosmic microwave background radiation. And so they named the WMAP program satellite after Wilkinson. So the W is Wilkinson. Okay, that's sort of an aside. Well, while they're getting their equipment together and designing it and getting set up, Penzias called Dickey and told him about this residual noise that they were detecting in their antenna system, in their radiometer, if you will. And Dickey, apparently, according to the conversation, this is what he says: we and they now believe that this noise, this residual noise that couldn't be accounted for in the system that Penzias and Wilson were using, and they decided that this was due to the cosmic microwave background radiation that had been predicted by the Princeton group. So it was I think the point of this is that Penzias and Wilson actually had been given a paper written, as I understand it, was a preprint paper that had been written by Peebles and had been circulated around. And somebody who had received this paper, I forget his name, gave this paper to Penzias and Wilson, and they read this, and then they began to think, oh, this might be what we have in our antenna. So that seems to be a more realistic idea of what really happened that caused them to discover the microwave. If you think of it as a discovery, okay, then it kind of makes sense from the point of view of the Princeton team were the people who really basically predicted this microwave background radiation, and they were beginning work on building antenna and equipment to detect it when Penzias called and said, well, we've got this background noise and we think that it might be this radiation that you're looking for. Okay, now I want to go back a little bit and talk about what people were thinking prior to what the Princeton group doing and the discovery of the microwave background radiation. And I looked at a couple of went through some books and looked. I have a book by McVitie, which is a book on cosmology. And most of these people were thinking in terms of the galactic radiation that had been discovered originally by Jansky in 1932, I think it was. And Reber had made maps. And so they had made maps of the cosmic microwave, of the cosmic radiation or cosmic radio waves. Okay. And the idea was, and they pretty much established that these waves came from the galaxy. And, if you look at the maps that are published, it's pretty clear that they were looking at radiation that came from the Milky Way galaxy. But in McVitie's book, he doesn't mention anything about black body radiation or cosmic microwave background. And Slavoski in his 1960 book also talks about the radiation from the Milky Way, but he doesn't mention anything about black body radiation or microwaves created in the hot Big Bang model. And in those days, they referred to the models as relativistic models. And Hoyle, and I read a paper by Hoyle where he talks about the status of cosmology just before the discovery of the microwave background. He's very much not interested in the relativistic models because he doesn't understand how galaxies can be formed if you have this expanding universe of hot gas. How does this expanding hot gas condense to form galaxies? And that becomes an issue later when we talk about the satellite experiments. I'm going to talk a little bit now about Penzias and Wilson and their antenna. This is at 4 gigahertz, okay, which in those days was a pretty high frequency, 4,080 megahertz, 4 gigahertz basically. And what they did was they measured the antenna temperature and came up with this number of 6.7 K. Now, these numbers come out of their paper that they published, the discovery paper. And they have a comparison technique where you switch between a helium-cooled load, okay, and you switch between the helium-cooled cold load and the antenna, and they record the amount of noise that they measure on a recording device. And from that, they can ascertain the temperature of the sky. Now, at this time, the idea was that they shouldn't really be measuring anything at all with the antenna pointed away into a blank part of the sky. We shouldn't see anything, okay? The antenna shouldn't be picking up anything in its main beam. The only thing it should be getting is maybe some noise from its side lobes. Now, this is kind of technical information. Now, the key to this whole thing is that they were using a Ruby maser that had a noise temperature of 3.5 K and 42 dB of gain. Now, I was a satellite communication satellite engineer for many, many years, and I can tell you that's really the most important piece in the whole story. They had a very high gain antenna, and it had low side lobes. But if you don't have a low noise amplifier at the front end, we call these amplifiers the first stage of amplification, low noise amplifier, or LNA. And the whole point of satellite communications that really makes it work is you want an antenna that's got low side lobes, so you don't pick up noise from the ground and the surroundings, and you've got a lot of gain, and you have a very low noise temperature amplifier, preamplifier in the first stage. And this maser, Ruby maser that they say, this I think is really the key to the whole thing about the discovery. It was a new technology at the time and had very low noise. So that really made this system a very good system for making this discovery of the cosmic microwave background. And then they did a calculation. They start off with 6.7 K is what they measured with the antenna, and made some corrections. There's a correction for atmospheric noise. It's not real clear to me exactly what they mean by that. And then ohmic losses, and they came up with the excess noise of 3.5 K. So Penzias and Wilson detected this cosmic microwave background noise, and they measured it to be 3.5 K. Now, we know that's too high. The current measurements show it to be 2.726. So that's not really too bad. I suppose you could argue that. All right. That was a pretty accurate. Now I'm going to talk a little bit more. The antenna was built for the Project Echo. I don't know if people remember Project Echo, where they had these, NASA launched these big silver-coated balloons into space, and they were used them for communications relay links. And this is basically the origin of satellite communications. The antenna was an offset paraboloid antenna and had a gain of 47.65 degrees. And this is a pretty sophisticated antenna, had a pretty much a high gain. So basically, NASA funded this project. And if you look at this tech note here, they talk about, they made very extensive measurements of the antenna. It was very extensively tested and proved out. And so they were using an antenna that was very thoroughly understood, its technical characteristics were thoroughly understood, so they could rely on their estimates of what the noise temperature of the antenna would be. All right. Okay, this is the paper that was when the discovery was announced, and I think this is a kind of an interesting thing. The Princeton paper, there were two papers published. There was a paper published by the Princeton group, and that appeared before, and if you look at the order of the papers published, the Princeton paper was published in front of the Penzias and Wilson paper. And so this is referring to, the name of the paper was Cosmic Blackbody Radiation, and it was published in May of 1965. I think it's really this paper that really establishes the cosmic microwave background and makes the prediction. But as I pointed out earlier, it's misleading when some of the sources attribute this prediction of the microwave background to the Gamow group, but it does, so I think that's kind of misleading and incorrect. Okay, also they don't use the singular origin hypothesis. They talk about the cyclical universe. And this is a quote: "It is the third premise is accepted tentatively as a working hypothesis that carries with it a possible resolution of the second paradox. For the matter we see about us now may represent the same baryon content of the universe, of the previous expansion of a closed universe oscillating for all time." So they're saying, in effect, basically, that they're making a prediction that the universe is a cyclic universe, it's closed, and it's oscillating for all time. That's not the accepted interpretation that exists today. And I'm pointing that out for the reason. Okay. And here's another quote: "Could the universe have been filled with blackbody radiation from this possible high temperature state?" So they're saying this is really the concept of the blackbody radiation. So they're making a prediction here. It's actually, but they're being sort of cautious about, could the universe have been filled with blackbody radiation from this possible high temperature state? So they're saying the universe collapses down, gets real hot, and then you get this hot, high temperature fireball that occurs, and then it re-expands again. And then here comes this is the theory. If so, it is important to notice that as the universe expands, the cosmological redshift would serve to adiabatically cool the radiation, while preserving the thermal character. The radiation temperature would vary inversely as the expansion parameter radius of the universe. This is really where this is the prediction of the blackbody the Big Bang blackbody radiation. This is, in my opinion, this is where it comes from. This is the source of it. This is where it's first really stated, and this comes from the paper published by the Princeton group. And of course, they referred to the Big Bang as a fireball. I like the big flash. And now the question is, it's pretty clear that this is really the prediction of the cosmic background radiation. It really comes from this Princeton. It's not really a paper. It's a couple of pages long. It's a brief description. And why isn't Dickey and the Princeton group giving credit? I mean, it seems to me they should have been given credit. And I find this rather curious as to why the Gamow idea, which didn't have a cyclical universe, that the universe emerges from this hot Big Bang with nothing happening prior to the Big Bang. That's the Gamow idea. And so I'm kind of puzzled by this. If anybody can explain how or why the Princeton group didn't get the acclaim that would appear that they would observe. Now, my thesis is maybe there was people who didn't like Dickey's scalar field theory, which was in opposition to the general theory of relativity. He was proposing a theory of gravity that wasn't in competition to Einstein. That's just one of my thoughts that comes to mind as to why they didn't get the credit. Okay. So here I'm saying, why was the Princeton team's idea discarded? Why was the cyclic universe idea discarded? They predicted the microwave background radiation. And to me, they solve a problem that we still have today, which is if you say if you go with the Gamow approach, the universe starts at some time t equals 0, and we don't really know anything about what happened prior to t equals 0. And that's kind of philosophically unsatisfactory. And it looks to me like the Princeton team had a better idea, and because it avoided this time would start at a certain point, and then the universe would emerge from apparently nothing. And so to me, that seems that's more of a philosophically satisfying idea. And I think that was kind of the way the Princeton team was thinking. And we do find here at the bottom, in 2019, James Peebles was given a Nobel Prize. He got 1/3 of the prize, but he wasn't really given the prize for, as I understand it and what I've read, he was given the Nobel Prize for his work in cosmology. So his work, all of his work, he published a lot of books and did a lot of work on cosmology and the advancement of cosmology, but it doesn't seem to me that they're citing him for the discovery of the cosmic microwave background radiation. Now, in Wikipedia, at the end of their article about James Peebles, there's a statement that James Peebles makes that supposedly came from his statement after he won the Nobel Prize. And he says that this was really the fact that they gave him the prize wasn't so much, he looked at it from the point of view, it wasn't him that was winning the prize. It was an acknowledgement of Dickey's idea and Dickey's leadership. And so Peebles, being a gentleman, is really basically acknowledging that Dickey was really the one who should have been deserving of the Nobel Prize. He didn't get the Nobel Prize. Dickey didn't. All right. Okay. So I think maybe I belabored that a little bit too much, but I tried to want to make it clear that some of what is said in textbooks and the way it's presented is kind of misleading. It's clear that and I find this, well, to go back a little bit, I'm kind of puzzled by the fact that the physics community, the astronomy community, all accepted the Gamow version, although Gamow didn't really make a prediction that led to the discovery. It looks more like the Princeton group really did that. Why did they accept the idea of the Gamow version of the Big Bang instead of the Princeton version of the Big Bang? Now, that to me, that's puzzling to me, and I don't really understand that part of it. That's why I sort of spent a lot of time talking about this. It's not really. By the end of the 1960s, it's pretty clear that everybody was believing, all the textbooks and all the experts were believing in the Gamow version and not really paying any attention to what the Princeton group had said. All right. I'd like to shift here to the COBE Cosmic Background Explorer. And this is when, for the first time, they came up with an anisotropy of the cosmic microwave background. And I'm going to show the map here. There's the COBE map. It shows the temperature variations. And I would have thought that this doesn't really go along with their black body theory too well. But they're basically being, good at. They've pretty much locked themselves into the Big Bang idea at this point. By 1980, this has been an accepted theory. They've made lots of measurements. They've confirmed that the spectrum looked like a black body, and maybe suspicion. At this point. We see here that they did detect an anisotropy, and the COBE did measure the CMB spectrum, and they claim they've got this tremendous precision, and they 0.03%, demonstrating the first time that it closely matches the black body with a temperature of 2.725 K. All right. I remember when the publicity came out about this, and it was all like the cosmic microwave background is confirmed, the Big Bang is proven to be true, everything fits. But these variations that wouldn't appear to be in support of a perfectly smooth cosmic microwave background radiation. So I think that's a little bit something that we should think about a little bit. Okay, so now we have the Wilkinson, the follow-on satellite, the WMAP Wilkinson Microwave Anisotropy Probe, and launched in 2001. And this is kind of a summary of some of the accomplishments that NASA talks about in their publicity. Determined the universe to be 13.772 billion years old. The Hubble constant, 69.32 plus or minus 0.8. That's all based on the lambda CDM cosmology. And here's another point. When I saw this, I thought it was pretty interesting because people had this comment that NASA claimed to have determined that the universe was Euclidean. And when I first heard that, I thought that's kind of, how would they do that? And that comes from the WMAP, the WMAP. And they claim that they nailed down the curvature of space to within 0.4% of flat Euclidean. That's pretty interesting. One would wonder how they did that. Then they claim to have determined that ordinary atoms make up only 4.6% of the universe, completed a census of the universe and find that dark matter is 24%. How did they come up with a number of 24%? That's kind of curious. And then they determined that dark energy in the form of a cosmological constant makes up 71.4% of the universe. How did they come up with these numbers? These are pretty clear-cut numbers. Here's the map of the temperature variations, the WMAP universe map. There's these variations, temperature changes. Okay, and I'm going to repeat this. The universe comprises 4.6% atoms, 24% dark matter, and the biggest fraction of it is this 71% of dark energy. You'll notice, different sources kind of give slightly different numbers. Okay, this is a repeat of that slide. Here's the pie chart. Okay, that shows the different makeup. Now, I kind of want to point out, here's a different pie chart. This was the pie chart that I used in my presentation 2 weeks ago. And the pie charts don't agree. Well, for one thing, in one chart it says 74%. And in the other one, well, here in the WMAP chart says dark energy is 71.4%. And then this other chart, it says 74%. So why are these charts different? That was one of my first thoughts when I first started looking at this, at these charts, and why are they different? You'd think they're coming from different sources. So, and you'll notice the chart here doesn't really say where the source came from, which kind of, you get stuff off the internet, and you think you're getting correct information, but you may not, and that's kind of what happened there. Here's the WMAP claims to approve in the inflation. The WMAP observations also support and add on to the Big Bang framework to account for the earliest moments of the universe. Called inflation, the theory says that the universe underwent a dramatic early period of expansion, growing by more than a trillion-fold in less than a trillionth of a second. Tiny fluctuations were generated during this expansion that eventually grew to form galaxies. So their idea is that those variations in the temperature are these variations. Let's go back here. Yeah, these temperature variations, and that's their idea of how galaxies form. Now, notice I deliberately mentioned Fred Hoyle's. He wasn't particularly expanding. Okay, so if the universe is expanding and space is expanding, how do galaxies contract out of this expanding gas that's the result of the Big Bang explosion? How do these galaxies form? How does the force of gravity act to form galaxies and create stars when the universe is expanding? And this is a problem with their whole concept. And they claim that the tiny fluctuations were generated during this expansion that eventually grew to form galaxies. That's their hypothesis. And it's kind of questionable whether or not this is really, I don't really find this to be particularly convincing, frankly. And so we'll leave it at that. That's a big challenge for the Orthodox establishment people. I think they believe that this is true because they've been told that it is. But for people like me, dissidents, maybe, we need more of a convincing argument. Okay. I'll talk a little bit about the Hubble constant. It puzzled me. How does measurement of the microwave background radiation give you the Hubble constant? And turns out if you look through the information, there's different values of the Hubble constant that you can find. So you have to be sort of careful about. So which value of the Hubble constant is the correct Hubble constant? And notice here I talk about one source tells me that WMAP found it to be 71.0 plus or minus 2.5. And then if you combine it with other data, and what other data are they talking about? You can get it down to 70.4 plus or minus 0.4. And, one of the things I noticed that these numbers that came from, Google search don't necessarily agree with what the NASA site said. So you got to be a little careful about the numbers and where do they come from. And then going to Wikipedia, they give different numbers based. So there are different results given for, they process the data after a period of time and they produce preliminary results. And then, so in the first year, they got 71 and 5 years later, they got 70.5. After 7 years, it's they got 7.4. I guess they're narrowing down the error ranges. And then they get a final result after 9 years of 69.32, which is the number that I think most people are, using. But you got to be a little careful about, where these numbers come from, what's the source. And it looks to me like, my comment is, I don't really understand. I don't know what they did. This is, they're measuring, making a bunch of measurements on the satellite, recording data, sending it to the ground, processing it on computers. How are they processing all the data? What are they using it for? It's not really clear to me. And as I say, I suppose I could do probably a couple of presentations. I could spend a lot of time. You could probably write books about how all this processing of the information is being done. Okay, so that's a repeat of what we talked about before. Here's a diagram that they show on their site that shows, this gives kind of a hint as to how they're using the data. And what you see here that they have a model. These are model prediction curves. And the model prediction curves are intersecting this vertical line. And so what they're doing is they're saying that this is kind of how they're getting their results, their numbers that they're claiming. We measured so much of this. They're taking measurements and comparing them to a theoretical model. The theoretical model that I believe that they're using is the Lambda CDM model. So this raises a question in my mind is, how do you know the Lambda CDM model is correct? Wouldn't you be using the satellite data to prove the Lambda CDM model? But that's not what they're doing. They're assuming the Lambda CDM model is correct and comparing it to measurements and therefore saying, okay, this is how much is dark matter, this is how much is dark energy, and this is how much is real matter. That's what I think that they're doing. Okay, and how are they doing this? They're measuring this thing called the angular power spectrum. And this is a chart that shows, and then it's more than just the WMAP. You'll see here that they have history data from others. The idea is, and if you go to the NASA site page, they have a little learning section where they say how to build a universe. And they give you some sliders down at the bottom. And what you do is you adjust the sliders that they have on the page, and you try to match the measured data with the predicted data that the model predicts. So that, to me, indicates that what they're doing is they're doing best fit of the data to an assumed model, and that's where these numbers are coming from. Okay, now it looks to me that Planck's a little later, it's in 2009, and basically did a repeat, it would seem to me, of what the WMAP did. But apparently, from what I gather, they had a more narrower beam antenna. So their antenna was more, if you say sensitive, or actually had better resolution, I think is the best way to put it. They had better resolution. And this is kind of a summary of their universe. Jim, if you could mute, that'd be nice. All right. And they come up with looks like a slightly different numbers than, the ordinary matter prediction doesn't look like that's, I don't think these numbers, so they're getting different numbers, basically. That's the point. So if you sort of have a choice as to what you're going to use. Are you going to use the WMAP results for the predictions of the contents of the universe, or are you going to use the Planck predictions for the contents of the universe? So I think that, to me, that's again, here we have different values. They publish different values for the Hubble constant. And they came up, I think, in the end with a number that's different from the number that the WMAP satellite came up with. And so I noticed that Vladimir uses the number 68.7457, which is pretty close to these Planck numbers here. The first number is 67.4, maybe a little low. 60. So maybe the Planck numbers are a little low compared to what the WMAP model predicts. And then the WJST, recently they published a value of the Hubble constant from different data of 69.96. So there does seem to be, a kind of a discrepancy, and this is called the Hubble tension, the discrepancy between the optical observations and what the satellites are predicting. But I have a question as to what is it that how are the satellites measuring the Hubble constant? They're doing a fit to a assumed model. Okay, a best fit to assume model. How are they processing the data? That's something that you need to sort of ask about. How are these numbers actually being produced, and why are there differences in the numbers? That's an issue for me. This is the Planck anomaly map. Now, one of the reasons I'm bringing this up is because there have been this anomalies. There's the temperature difference between the hemispheres. That's pretty well known. And I thought this was kind of interesting, worthy of note. They made a statement about the anomalies and said, but hidden in the detail provided by Planck, there was also a hint of something more fundamental beneath the surface. A number, and I put this in bold, a number of anomalies in the data do not perfectly agree with the predictions of the standard model. Now, I'm assuming they mean the lambda CDM model. Some of these anomalies were found for the first time in the Planck data, while there had been evidence of others in previous experiments. Theoreticians continue to speculate about the implications of these anomalies and to investigate possible ways of extending the standard model. So it looks to me like there's these anomalies, but they're going to try to figure out ad hoc ways of explaining them and keep their standard model intact. Okay, then there's the axis of evil problem. And there's been a lot of publicity about this. You know, I can't say that I understand perfectly. It's about the axis of evil is a name given to the apparent correlation between the planes of the solar system and aspects of the cosmic microwave background. It gives the plane of the solar system and hence the location of Earth a greater significance than might be expected by chance, a result which has been claimed to be evidence of a departure from the Copernican principle as assumed in the concordance model. So they're talking about the cosmological principle, basically. It violates the cosmological principle. And so this data also, this problem of the axis of evil also, it shows up in the Wilkinson microwave anisotropy, WMAP, and the Planck mission. They tend to agree on this issue of the axis of evil. So that's not been resolved by the data. Better data didn't resolve that. And data from the Planck telescope published in 2013 has since found stronger evidence for the anisotropy. For a long time, part of the community was hoping that this would go away, but it hasn't. In 2015, there was no consensus on the nature of this and other unobserved anomalies. And so you can go to Wikipedia, these are quotes from Wikipedia, and find out more about it. This is a problem. Okay, kind of my idea about this is that this idea of what they're doing is kind of a tautology. They're convinced that the theory of the Big Bang, that the universe was expanding, and therefore they were convinced that perhaps this was a good explanation. The only competing model was the steady state model that Hoyle and Gold and Bondi had advanced. And that had been some of the results that had been published by radio astronomers claimed to have refuted the steady state model. And so this, at that time, this was, the Big Bang was the only, it's sort of like, we don't like the steady state model, but there's problems with these quote, relativistic models or Big Bang models. And so when they discovered the microwave background radiation, when that got published, it was very natural for them to assume, oh, yes, this proves the Big Bang. And so they jumped on that bandwagon. But I'm not really convinced that this is really the case. To me, it seems kind of like circular reasoning. You know, you made an assumption that the universe is expanding, and then finding something that your prediction is based on assuming the universe is expanding. And so it strikes me as a tautology. And so I'm not particularly convinced of it. All right. So basically, my view of what they've done is they haven't found a contradiction with the assumed standard cosmology. So it's good. They verified it in the sense that they didn't falsify the standard model. That's basically kind of my view of it. And it's not real clear to me that in the case of that they're using the model, the model that they assume to be correct, they're using that model to make predictions about the contents of the universe. So it doesn't seem to me that they're really basically validating the model. They're just using the model to make further predictions. Okay. When I found this out, this kind of surprised me. Garrett Verschuur, who is, I always thought he was an orthodox guy, scientist. has expertise in radio astronomy. I have a couple of his books, and reading his books, I always had the idea that he was an orthodox guy. But he's come up with an objection to, he doesn't think that this radiation that they're measuring is coming from the Big Bang. He thinks it's a local radiation. He said he has noticed that the temperature variations recorded by WMAP tend to coincide with radio emissions from neutral hydrogen in the Milky Way. In other words, the fluctuations may not be part of the CMB at all. Okay, so these measurements that we looked at, if you see the charts with the temperature variations on it, he's saying those variations aren't due to the microwave, due to the black body radiation from the Big Bang. They're not evidence for black body radiation, thermal radiation from the black body when the universe erupted in its fireball or big flash, as I like to say it. He says that it's, created by local matter, okay, that's close to us in the Milky Way. That's what he's saying there. And so Verschuur made his discovery while studying the Leiden, Argentina Bonn LAP survey, a map of radio emissions from neutral hydrogen in the Milky Way that was completed for the entire sky in 2005. So that was the basis of his, and he was, looking at these maps of neutral hydrogen and then looking at the CMB maps, and found that there was a correlation. In his paper, Verschuur notes 6 areas where he has found visual correlations between the lab, the Leiden, Argentina Bonn survey, and the WMAP satellite survey, though he says that he has since found around 200 more correlated areas. It's kind of interesting. He's not going along with the accepted orthodox interpretation of what the satellites were measuring. And then I have a comment. This is a comment I have put on here. I've been wondering if anyone had tried to correlate the CMB WMAP with other maps of the universe to see if they coincide. And, it just struck me as kind of like, how do you know that these fluctuations that you're observing with the satellite data aren't caused by distant galaxies or local associations of stars or emission nebula in the Milky Way and stuff like that. And, I was thinking about that, and so then, here's this guy, Garrett Verschuur, he actually did it. I was wondering if anybody had done this, and he actually did it. Of course, his results are, okay, that's a repeat. Okay, now I'm going to, I was talking about this last week, and somebody asked me about Pierre-Marie Robitaille, and he claims that the radiation, that the CMB radiation comes from the sun, and oceans of the earth. And I'm not really sure I understand exactly what he's saying. And it's not real clear to me that these statements that you find, if you go to Wikipedia and go on the internet, that they're really basically presenting a valid account of what he's talking about. But I know that I've seen some of the videos that he's put on the internet about he disagrees with the standard interpretation of the microwave background radiation. So there are people who, dissident scientists who disagree. And that's really what I want to point out. Okay, so we're getting now towards the end. And I want to bring up this conformal cyclic cosmology that is, and apparently this has been around for a while, since about 2005, I think. proposed by Roger Penrose, who's a Nobel Prize winner, worked with Stephen Hawking. And so this guy is, he's I would say pretty well establishment scientist. I use the word establishment. Used to use the word mainstream. I can't really describe him as orthodox if he's proposing something different. Now, he proposes a cyclic universe concept, and I think his thinking is sort of similar to the thinking of the Princeton Dickey and the Princeton group, where you have this problem of how do you explain origin in time? Why does time start at a certain point of time, t equals 0? Where does the energy come from to create the universe? What existed before that? And so this conformal cyclic cosmology, I believe, is sort of an attempt to resolve that problem. And I think that from what I've seen about Roger Penrose, he's kind of become a philosopher, and not so, he started off as a mathematician and a theoretical physicist, and now he's sort of moved into being a philosopher. And there are a lot of, there are a lot of videos on the internet that you can go to find out about what he's talking about. I watched some of them, and I really couldn't really quite grasp exactly what he was talking about. He talks about black holes. What happens to black holes at the end of the universe? Do they disappear or whatever? I found that kind of confusing, but apparently a lot of what he's thinking about has to do, well, remember, of course, he got a Nobel Prize for his work on black holes with Stephen Hawking. So he's thinking about black holes and what is the ultimate fate of black holes in the universe. And so he has this concept of his cyclic universe concept is that each cycle is an eon, and this is a diagram. This kind of interesting. This was the best explanation of what he's talking about. Now he's doing something that in topology they call identification. That is where you identify, or some people use the term glue. You identify a topology. So he's identifying the Big Bang and the expanding universe on the left, and at the bottom, and he gets this conformal time, what he calls conformal time. So time on the left is, what you normally call, which is like, I guess, the standard concept of time that is used in cosmological models. He's using conformal time on the right. And he identifies the Big Bang at the bottom, okay, with the bottom of the cylinder on the right, and he identifies the end of the expansion on the left with the top of the cylinder on the right, okay. And then by doing that, he gets these successive eons, okay. So the eons are the eons are mapped onto this progressive continuous universe. So the universe is now, it's infinite and continuing. It doesn't have a beginning and it doesn't have an end. And I think this is more like what the Princeton group was driving at. And so the question then is, is he going to have more success? I doubt that he's going to be, he's been promoting this theory for a long time, this cyclic universe theory for a while. I don't think he's made a whole lot. I don't think it's been accepted. I think everybody's still hanging on to what they call the standard model of the lambda CDM model. Okay, so here are my final thoughts. The conclusion that the CMB, or the cosmic microwave background, is a remnant of the Big Bang or the Big Flash depends on a belief that general relativity correctly describes the nature of the space-time metric. So you have to have this idea that the universe is expanding. To me, I have a problem. I don't know what is expanding. Okay, that's a problematic thought there. So you have the universe is expanding. Then they dismiss other ideas. Like, for instance, I talked about the Jarrett Verschurer, that the cosmic microwave background radiation, he's saying that, well, it's coming from molecular clouds in the galaxy. It's not a remnant of the hot Big Bang fireball. Okay. And then my third, this to me is scientific conventionalism, which is that you're sort of, in order to progress in the scientific world, you have to believe in the Big Bang, because, and it's not real clear to me that they've really proved that the cosmic microwave background radiation was produced by the Big Bang. I don't think that's really 100% nailed down as true, but I think if you want to be a scientist and make money and get jobs in universities, you have to adhere to that thought. So that makes it scientific conventionalism. You have to adhere to the beliefs, and that's the established belief. Although it's not really clear to me how that belief got established, because if you look at the Princeton group, they made a prediction based on a cyclic hypothesis of the origin of the universe, not the Gamow concept of once only, beginning at t equals 0 and the universe going off infinitely. And how did that come about? Why did that arise? It's not real clear to me. I think it might have been due to the fact that Gamow was a pretty good self-promoter of his ideas, and that's kind of my thinking on it. Okay, now in my view, this is sort of an example of post-diction, in that if we go back to the beginning of where I started, the story that they're telling is a story that has been constructed by hindsight. So the story as they tell it makes it look like the discovery of the cosmic microwave background indeed does prove the Big Bang hypothesis. But when you start looking at the details, it doesn't really seem, all the details don't really seem to fit. So I think that what they're telling us in books and on Google and these places is kind of a form of recounting the events in hindsight that makes the outcome seem to be undoubtedly correct. And I think Roger Anderton, who is not here, would call that goalpost moving. Okay, so we're back to goalpost moving. Okay, so that's the end. Thank you very much. So we have any comments?
Yes.
Go ahead, fire away.
Okay, this is Nick. Yeah, I thought it was a great presentation, and I liked your, account of the history plus your twist that we see the same thing if we talked about the history of special relativity. The physics academia has this fixed theory, and every time we come up with some disagreement with the empirical evidence, it seems like they don't even entertain the idea that maybe the theory is wrong. They just say, oh, okay, how do I adjust the theory? What do I have to add on to it? And normally they do that by fiddling around with math versus physics. I'd like to just go on one topic, and that is, in the theory of the Big Bang, the problem was, and you allude to this throughout, that that would imply that everything should be totally homogeneous in the universe. I mean, that doesn't mean that there wouldn't be any local variations like planets and galaxies, but there wouldn't be major problems. And to correct that, someone came up and found a way to do it, and that was the period of inflation, which, as you said, there was a trillion times a trillion, or a trillion expansion in space within 1/trillionth of a second. And there was never any explanation of what caused the beginning of the inflation period or what caused the end of the inflation period. It's just there was this problem of too much homogeneity, and someone found a math solution to say, oh, okay, whatever minor variation there might be, here's this period that multiplies it by a trillion times a trillion times a trillion times a trillion, and that solved the problem. And then we had Smoot come along, and he wrote a book, Whispers in Time, and the whole thesis of his work was to look for reasons why there was this lack of total homogeneity. And his goal was to find some inhomogeneity, whatever it is, in the data. So he began looking, and I don't remember the exact numbers, but this is from his book, his account. And I'm not trying to cast aspersions on him. He was a very intelligent and honest scientist. But this kind of, what I found from reading his book was exactly the same type of inherent distortions that was found by, I'm forgetting his name, who wrote the Higgs fake at the micro level. And that is, in both cases, they are looking for a specific thing. One, on the lower level, it was the Higgs boson. On the higher level, it was more lack of homogeneity at the beginning. And it just struck me reading Smoot's book before I even read the fake Higgs. There was so much data, and they initially thought they could find the signal that they were looking for in 1 part in 100. They didn't find it. So they went to look for 1 part in 1,000. They didn't find it. I don't remember exactly how many orders of magnitude it was, but they went to 1 in 100,000, and there they found this signal. And by the way, they have an absolute ton of data and have the software to remove everything that doesn't look like the signal. And the other aspect is that if you don't find Higgs boson, or if you don't find some inhomogeneity in the initial Big Bang, you're a failure. You're a failure. But if you do find it, you win the Nobel Prize. In both cases, the guy who found the Higgs prize won the Nobel Prize, and Smoot won the Nobel Prize. And both were claimed widely as the discovery of the century. So there we have a lot of explanation of why currently accepted theory continues to be currently accepted despite the empirical data arguing against it and implying a major shift in the paradigm. And by the way I look at Verschure's data is that he, in coming up with these relatively local anomalies, is explaining the more inhomogeneity that's a problem. So I would expect him to be an adherent to the theory, and he's going to say, okay, basically the CMB is the radiation, and the reason why it's not as homogeneous as you'd expect is, of course, you have these local anisotropies because of your local position. And actually, Robitaille, though, went a little further. He was saying that the main cause of the CMB was from local things like the Earth's oceans. Okay, that was just my point about homogeneity and lack of homogeneity. Give a little history on that.
Well, I think my reaction was more or less, I was more or less looking at this from the point of view of people had asked during our cosmology group, what is the CMB? What are you talking about? And the more I thought about it, the less I understood.
Yeah.
And that's the more I looked into the whole issue of the CMB, the less sense I could make out of it. So it looks to me like it's better off if you don't question and you don't really try to dive into the details to understand what it's about. Because if you do, you just get confused in the maze of all of the details. Like in just even looking at the history, I thought the history was kind of, when, looking at the history and going like, well, this guy doesn't agree with this guy over here, and something sounds fishy, and my solution to the problem was to just ignore Gamow and go with the Princeton interpretation, which I think makes more sense. But all of the official discussions, they all want to make it look like that the Gamow made the prediction of the cosmic microwave background, and then that was proved out by the accidental discovery by Penzias and Wilson. And so it all seems like serendipity that proves out that, yes, indeed, there was this cosmic microwave background radiation produced by the hot Big Bang fireball. So it all looks like it's inevitably true.
Right. I certainly agreed with your thesis of having a lot of skepticism.
Well, what I thought was interesting was that Roger Penrose isn't buying into the orthodox view. He wants to have a cyclic cosmology, and I think he sees that there's a problem with this Big Bang. Everything begins at some point in time, and there's no valid explanation of why you just can assume some initial conditions and then solve differential equations based on your assumed initial conditions.
Yeah, exactly. But it seemed to me that Dickey and company were thinking about, the Earth starting off, or a cycle starts off with the universe being very small and sort of explodes, and then it begins to contract down to a small point where the heat becomes so intense that it explodes again or expands again. And I didn't see that aspect, at least in the picture, of what Penrose was talking about.
Yeah, his theory is, I I really can't say that I understood it. I just tried to give an overview of it. The point from my idea was that Penrose is proposing this, which seems sort of not really plausible. When you look at his diagrams and listen to what he says, it doesn't seem very plausible. So why is he proposing something that really probably wouldn't be accepted by his peers and colleagues? And other than, my thought is that he's disturbed by this idea of a beginning, an origin in time.
Right.
I think he finds that philosophically unacceptable, and he's looking for a solution to that problem.
Right. I've always thought it was philosophically unacceptable. And I kind of like the Dickey resolution of it. Not bad. And actually, I also like Vladimir's reconciliation. There are two different reconciliations, but at least they get rid of that problem. So I'm keeping an open mind on those.
Is the conventional thinking for the believers in the Big Bang that the CMB energy coming in represents a signal that has been traveling for some 13 billion years? And I guess the answer to that question is a yes, right?
Correct.
And well, if that's the case, how do you determine how long a signal has been traveling with the data detected? How is that determined?
Good question. I don't think there's a determination of it. I think it's I think they believe that the radiation is caused by the initial big flash, as I like to call it, and that big flash produced black body thermal radiation, which that in and of itself I find kind of hard to swallow down and believe is true. And they believe that that's true, and that as a result of that, the radiation would be shifted in apparent temperature to 2.7 K. So you're starting out, I don't know what the temperature that it's whenever there's this what they call the era of recombination, I think they call it, which is misleading. It's when the fireball or the fireball becomes transparent to radiation. And so when after that era occurs, then this black body radiation spreads out and is no longer in equilibrium with its source. And I never really could understand how any of that made sense. I couldn't understand how, the way they describe it in a lot of the books, I think people misunderstand. But I think really what it boils down to is they're saying that when they Penzias and Wilson, when they were looking at a region of space that didn't supposedly have anything in it that was radiating, that it was looking back 13.5 billion years in time and seeing the original big flash, the remnant of the big flash. So they're in essence saying, yes, they're detecting the original Big Bang flash.
Okay, James, here's my take. If you have a gas or whatever at a certain temperature and it's in a really compact container, and then you mathematically assume the container expands first by a trillion times a trillion times a trillion times a trillion, and then continue to expand, just using laws of gas in a container, the temperature would drop. Yeah.
Yeah, that's the adiabatic expansion idea.
Yeah.
I've mentioned that, and the Princeton, when they did their original publication, they talk about that, and he says the adiabatic expansion and the red shifting of the radiation. I think it's actually the red shifting of the radiation that's really explains the low temperature of the Big Bang. So the radiation is red shifted, meaning that it's shifted down in frequency from the very high frequency that it starts off with, and then it's red shifted down due to the expansion of the universe, which causes the redshift. That then begs the question of, do you believe that the redshift is caused by the expansion of the universe? And what does it mean to have the universe expanding? What's expanding?
Okay, well, on another question, comparing these maps of the different satellites, the WMAP and so forth, the Planck map and the different ones, are they all using the same coordinate system? Some sort of an absolute reference?
I believe that would be I believe that they do.
Or coordinate system that's the same in all.
I think that's the case. Yes.
They are using the same, so you could overlay the different maps.
They're using what is called galactic coordinates in the presentation of their maps, and those maps, you'll notice that they don't have the Milky Way in there. The Milky Way is right in the center of those maps, but they've apparently figured out some way of removing the Milky Way. And that's what's left. What they show you is what's left after they've removed everything that they think is not the cosmic microwave background radiation. So they've removed everything that they don't think represents the cosmic microwave background.
So in terms of the microwave frequencies observed, are these theorists claiming that over some 13 or whatever billion years of travel, there has been some sort of a red shift, and that it was actually originally a much higher frequency radiation? Or does that make sense? I'm trying to make sense of this myself.
Well, it's a black body radiation, but at least in Harry's presentation, they were talking about a cooling. Okay. So that as the universe expanded, then whatever is giving off the black body radiation would tend to cool.
Yeah, that would be what.
Assuming that the signal has been traveling for billions of years to arrive at the antenna, I've designed FET input, high impedance input devices with low noise amplifiers in my neuroscience lab, and I'm very skeptical about this whole noise analysis. In other words, the assumption that this particular noise is due to a signal that originated billions of years ago, as opposed to just more immediate sources.
That's a good point. And I don't think, to me, they haven't
including
really-
the amp itself. You know,
well,
the amp itself could be a source.
as I pointed out, being a satellite communications engineer, I understand this technology, and it's all based on, excuse me, it's all based on the noise temperature of your first amplifier, basically. So you're going to get some pickup from the antenna, and you're going to get, so there'll be noise that enters into the antenna, and the noise in the antenna enters two ways: through the main beam of the antenna, the pencil beam, the main beam that's looking out at the sky. And then there's a lot of radiation that comes in from the side.
Uh-huh.
Okay? And the radiation that comes in from the back. And what you do in satellite communications is you tell the manufacturer of the antenna, I want low side lobes. I don't want any radiation coming in from the back. I only want radiation that comes from the main beam. And so it's possible to design antennas that minimize the noise that's coming in from the side lobes and the back. And so you're trying to get, and that's specified by what's called the noise temperature of the antenna. So the assumption is that if there's no noise in the main beam, what's the noise coming in from the antenna and its environment? And in the slide that I showed about that, they claim that it's 2 degrees K for the Homdale antenna, which I think is kind of low. But so the main noise that you're picking up is going to be coming in through the beam of the antenna, what you're looking at with the main beam of the antenna. And there's noise coming from there. It's what you're looking at in outer space. What is it that you're looking at? And then the other noise that gets added in is the noise from your low frequency amplifier. And then the amplifiers further down the chain. But the noise of the low noise amplifier noise is the main contributor to the noise. And if you have a very high gain, low noise amplifier, you can get that noise down to a very low value. And that's what makes satellite communications work. That's the whole key to the whole thing, is you have an antenna with a very high gain pointing at a place in space that isn't creating a lot of noise. So when you're pointing your antenna at the satellite, there's not a lot of noise around the satellite that's coming from the cosmic microwave background radiation and that sort of thing. And so the signal from the satellite is being received, and you have a low noise amplifier and a high gain antenna, and that's what really enables you to receive the signal from the satellite.
Okay. Now, another question. Wouldn't the anisotropy in these maps be far greater if there was a big bang or a big flash located at some point in this coordinate system of these maps? In other words, some detection of a center or a source of the signal, but the fact that these maps tend to show fairly even radiation depending upon whatever direction you look seems to negate the idea of a big bang or big flash in the first place, does it not?
Well, I'm not sure I understand.
Basically, the question is, why don't these maps show a greater anisotropy if, in fact, the original signal of this cosmic background radiation is located somewhere in space, a specific place in space where the flash occurred from, the origin, if you will. In other words, I'm questioning the Big Bang Theory. I think these maps are actually showing that could not have happened.
Yeah, you can take that point of view. I think the point goes to what I was saying. that they're interpreting everything so as to prove the Big Bang or to validate the Big Bang. They're not looking to invalidate the Big Bang. I think that's the whole point. They're looking at the data as proof that there's a Big Bang. They're not looking at the data to say, does this falsify our ideas or our thinking in any way? They're not doing that, I don't think. And in the case of Garrett Verschuer that I mentioned, and he's probably not the only one, they're not accepting his analysis because they want the Big Bang to be true, and they can't accept any contradiction to that.
Understood, because it looks like these maps are actually showing that are the best evidence that there was no Big Bang.
Is Verschuer explicitly saying this disproves the Big Bang? I thought he was trying to address arguments against the Big Bang.
I'm not really sure. What he's saying is that, as I understand what he's saying is, he's saying that the temperature variations that they're measuring are due to local neutral hydrogen clouds. So he's saying the maps, and don't accurately reflect the microwave background radiation. The interesting point is that they're saying that the orthodox people think that he's questioning the Big Bang by saying that. And so Jim is saying, well, that would actually be, in support of the Big Bang, because that would eliminate the fluctuations.
Yeah,
I think this whole issue is kind of confusing, and in that one of the things I never really thought, one of the reasons I don't understand how at this, let's go back to what they're claiming. They're claiming that at this recombination, at the end of the period of recombination, I think it's called, and I'm going to give you a technical term, where the universe becomes transparent to the radiation. Okay, there's this concept called optical depth, which is when you look through a cloud and, like for instance, the fog, you can't see the house that's next door. That means that you have a small optical depth. You can't see very far through the cloud. Okay, so what they're saying is that when this recombination or this era of recombination ends, I don't like that terminology, but that's when the universe becomes transparent. Okay, that's when the radiation is no longer absorbed locally in the big fireball. Okay, and the fireball becomes transparent. And they claim that once that happens, then there's a black body radiation that can be observed by us, because the universe is now transparent. So we look back in the universe to where the universe ceases to be transparent. And when that happens, that's when the black body radiation manifests itself to our measurements. Okay. The problem I have with this is, why should it be perfectly transparent? There are no spectral lines, or anything. Why is the Big Bang perfectly, they measure a perfect black body radiation. I mean, it's perfect. And it would seem to me it ought not to be perfect, which is, I think, your point, right, Jim?
Yes, exactly so. These maps should be showing an incredible anisotropy. And like if Vlad were here, he'd be saying, there is no center. And, like, where is the center? It should show up in this map as a brighter area, should it not?
Well, I think the anisotropy is attributed to the motion of the galaxy.
I don't know why you're thinking, Jim, that the Big Bang should be anisotropic, because all the discussion on this topic was It should be totally isotropic, but we're getting perturbations or anomalies to the
So now
expected
the Big Bang
homogeneity.
is not some sort of an explosion that occurred at some point.
It's a homogeneous explosion.
What is a homogeneous explosion, if I may ask?
It's
What
it's
is
when
that?
you have everything packed into one trillionth of a trillionth of a trillionth of a trillionth. Then everything should be the same. You get boom. I'll tell you, their expectations were that it should be homogeneous, and the fact that it wasn't is causing them all sorts of problems. But they tried to solve it by this mathematical trick of the period of inflation, and people like Smoot claiming to see these tiny, tiny, tiny whiskers in time, these little inhomogeneities when they look way back in time.
So the Orthodox people are now claiming that the Big Bang just sort of happened everywhere.
Yeah, everywhere at the beginning, which was like the size of a pea or something.
Unbelievable. Okay.
I think even in this short discussion, some questions have been raised that I never really could quite, some of the things when I read in textbooks that I couldn't really quite understand what they were talking about. And I had a problem trying to understand how the if the universe was expanding and the radiation was being cooled adiabatically. I could never really understand what that meant. And so maybe a lot of the issues are really that the textbooks and the people that are trying to explain these ideas aren't really doing a very good job of making them understandable.
Well, okay, the signal is back. Before the time runs out here, I think that we should really compliment Harry Richter for a very good historical analysis, and
Yes.
I'd underline analysis. He not only went in and explained sequentially, sort of, what publications occurred and what they said, but also had a wonderful analysis of the credibility and the veracity of this whole story. And so thank you, Harry. Great job, man.
All
I
right.
agree 100%. Thumbs up.
I'm glad you guys enjoyed it. All right.
Yes.
All right. I'm going to sign. So my final thoughts are, this is an example of, from my point of view, is if you don't really look at something scientific very closely, if you just accept what is said in a textbook, you might get the wrong idea. But when you look at it in detail, what you find in a textbook, let me put it this way, sounds good on the surface. But when you look at the details, when you start actually analyzing and you go to the primary sources, then the story doesn't seem as credible as it is presented in the textbooks.
Right.
I call it the fake science news.
Okay. All right. Well, thank everybody for attending. I'm sorry about the confusion at the beginning. Apparently, I needed to restart my computer at the beginning, and I didn't do that. And I got last week's video, which is kind of confusing. So I apologize for messing up. Okay, thank you, and good.
Take care, guys.